In this video, we're going to talk about enthalpy. So enthalpy is a quantity that is related to the energy of an object, but it's not quite the same. So enthalpy is given by the letter H, and it is equal to U, the internal energy of the object, plus PV, the pressure multiplied by the volume of the object. And what enthalpy takes into account is essentially the work that is required to place an object inside of a pressurized environment. So for example, imagine that I want to make something like this bowl. And I'm not going to carve it out of a tree, right, that already exists. I'm going to make it out of nothing, right? I'm just going to magic it into existence. So there's basically two things that I need to do to magic this bowl into existence in this room. Outside of learning magic, of course, that would be step one. But the other two steps would be, one, I need to add in all of the energy contained in the bowl, right? So I need to create all of the atoms, and I would need to bind them together in this way, and then I need to heat the bowl up to the room temperature, right? So that is the internal energy stored in the bowl. That's my U. But I would also need to do work in order to displace the atmosphere that the bowl is currently displacing, right? You can think about this if you've ever pushed something down into the water, like a floaty toy in a pool. If you push it down, you are doing work in order to displace the water around where that floating toy would be, right? That takes energy. You had to do work to do that. Just like that kind of pushing something into a pool example, if I wanted to place this object in a room full of air, like I'm in, I need to do work to displace the atmosphere where the bowl exists. That is P times V. You could think of this as the integral of P dV, where you have a constant pressure, right? And you integrate over the entire volume. So it just turns into pressure multiplied by the volume of the object. Now, this is useful because this tells us essentially how much energy would we get out if we could make the object completely disappear. That is, if we could use up all of the energy stored in the object itself, and we could get the energy back from collapsing the atmosphere to take up the space that the bowl used to occupy. Now, as with all energy type quantities, we're not so much interested in the absolute value of the enthalpy. We won't quote the value of the enthalpy of objects very often, but the change in enthalpy is very useful, right? In general, we talk more about changes in energy than we talk about absolute values of energy. And in general, we will talk about changes in enthalpy more than absolute values of enthalpy. Okay, so if we take the change in the enthalpy, so we just take a tiny change in enthalpy, well, we just apply the multivariable chain rule to this expression. So du is the first one, and then we have pdv plus vdp, right? We need to take the derivative of the first times the second, plus the derivative of the second times the first. That's our multivariable chain rule. And it turns out that enthalpy is very useful if we apply it at constant pressure. We don't have to have constant pressure to use enthalpy. It just happens to be very useful to be used at constant pressure. So what we're going to do is we're going to assume that the pressure is constant here, and we're going to set this term in our enthalpy change equation equal to 0. Okay, next we're going to turn to our du. So we're going to try to get du out of our change in enthalpy equation. So we can say du equals Q, the heat added, plus any work done on the system, plus any other work. Now, up to this point, we've basically only talked about compression work, but there are other types of work. For example, there is the work that is done by chemical bonds. So if you, for example, freeze water, there is energy released by the water as the molecules fuse together into ice. So that would count as other work. It's chemical work of the atoms bonding together. So we can write du in terms of these three things. And if we look now at dh, the pdv here cancels the minus pdv there. So our work done by the environment, our compression work, cancels out, and we're left with only heat transfer and other types of work. So it turns out that enthalpy is really useful if you think about chemical reactions or freezing or boiling of substances, because it tells you how much energy is released from those processes or is absorbed by those processes, ignoring the compression or expansion of the environment. So chemists often will make tables of the enthalpy change of a certain process. One example of a chemical reaction where enthalpy is an important quantity is the fusion of hydrogen and oxygen to make water. So we take two H2 molecules, we have one O2 molecule, and then we get two molecules of water out, plus some amount of heat. That heat is the difference between the energy of the two molecules separately and the fused molecules together. And this heat is given by the change in enthalpy of the system, right? So this really we could consider in the work other category, because it is energy that came from the work done in bonding these two atoms. But in general, we just kind of group these two, Q and work other, together, and we just call it the change in enthalpy. We can figure out how much heat is given off by this process by looking at the change in enthalpy of the process. So we have, from page 404 and 405 in the book, we have the enthalpy of each of these individual molecules. Now, the enthalpy of these two is 0 because these are the most stable, lowest energy states of these particular atoms. And so we basically use that as the 0 point of our enthalpy, and we measure all enthalpies from that 0 point. So when we combine those two atoms to get H2O, the change in enthalpy is negative 286 kilojoules per mole. The minus sign means that we are giving up heat when we do this. So heat is, in a sense, removed from the system by this process. That means that it is exothermic and it's going to heat up the environment. So remember, if Q, our value Q, is the heat that is added to the system, but in this case, the system is giving up heat to the environment as it goes through this exothermic reaction. We should also note that these tables are made where the reactants and the result are in the end at the same temperature. So say they start at 300 Kelvin, they both end at 300 Kelvin, right? And if we're not going to increase the temperature of our system, right, increasing the internal energy, that heat must be released to the environment. And that's why we get this negative value here, because any energy that is released here gets pushed into the environment to heat up the environment so that our reactants start and end at the same temperature. As another example of using enthalpy in a chemical reaction, let's look at the following reaction. So we have ammonia plus oxygen goes to nitrogen dioxide and water. Now, the integers out front here are just so that we have the same number of each type of element on both sides of the equation. So for example, if you look at the nitrogens, we have 4 nitrogens over here, and we have 4 nitrogens over here. This is just balancing the chemical equation. Okay, so what we want to do is figure out how much heat would be given off or absorbed throughout this process. To find out the change in enthalpy of this reaction, we have a table here. We have the enthalpy, the small f stands for the enthalpy of fusion, the enthalpy to create this compound out of the most stable possible compound for each element. So, for example, oxygen again has a enthalpy of 0 because this is the most stable form of oxygen. Okay, so what we're going to do is we are going to plug in the enthalpy values for each of these elements, and then we're going to see the difference in enthalpy between the two sides of our equation. So here we have 4, so we are going to combine 4 moles of ammonia here. So we are going to say 4 moles multiplied by negative 46 kilojoules per mole. So notice that we end up with units of just kilojoules because enthalpy has units of energy. Plus 7 times 0. And then we have on the right-hand side nitrogen dioxide with a delta H of 34, and we have 4 of those, so we have 4 moles multiplied by 34 kilojoules per mole. And then finally we have 6 oxygens, and oxygen has, 6 water molecules, and water has a delta H of 286, negative 286. So we will subtract 6 times 286. We can find the total change in enthalpy of this process, and in turn find the total amount of heat given off or absorbed by the process by taking the delta H values for the reactant, for the resultants of the process, and then subtracting the delta H values of the reactants, the initial molecules that we had. So this leads us to 4. Now, I will avoid writing the units here for this part just to save space. So 4 times 34 minus 6 times 286. That is the right side here, and then we are subtracting 4 times negative 46, and all of this leads to negative 1396 kilojoules. So the amount of energy given off by this reaction when we combine this many moles of each of the elements is given by this value. The fact that it's negative tells us that this is an exothermic reaction. It is giving off heat into the environment as this reaction happens.